Good morning, everyone. Can y'all hear me okay? All right. We got 8 people in here. Get started in just a second. Audrey, I was confused by the name a minute because I didn't look over at the up under the screens, and I was looking down the side. I was like, "Who is Trevor Welch?" Now it makes sense.
Our newest member.
Yes. Oh, cool. Yeah, I was just trying to look at attendance real quick, and I saw that, and I actually flipped back to my Slack. I'm like, "Who is this guy? I don't have him in my Slack." But I got you. Glad to see you got on.
Yes.
All right, we are going to go ahead and get started. So, share my screen. Okay, so the first 2 days we have been going over the data structures. We went over singly linked lists. We went over doubly linked lists the other day. Your assignments, your individual projects have included a queue and a doubly linked list. And if you've gotten past that, the point you are at right now, if you're following the order, is the binary search tree. So I've got an example of that data structure up here on my screen, but who can just in real general tell me what a binary search tree is? Everybody should know from the video. Just put it in whatever words come to mind. What is a binary search tree? What does a binary search tree utilize for efficiency? What sort of concept? Real general, broad concept. Patrick. Today the code isn't so long, so I'm going to ask quite a few questions, and I will let it sit silent literally for a short bit if nobody speaks up until I speak up, because I want everyone to get their time's worth and money's worth. So like I said, the code that we're actually writing out is pretty short, so be a lot of questions. We'll refer back to some Python syntax. Smaller numbers go on the left, larger on the right. Yeah, in a general sense, that is exactly what we're doing. We start with a root node, and as we are populating this binary search tree, you can imagine each of these being a node, a data point with a value. And as it comes in, really you can put less than or equal to, or less than and then greater than or equal to. That's a personal decision. We'll do it with less than and greater than or equal to, but you're putting the smaller on the left and the larger on the right, and you're having to decide which side to put if there are equal values possible in that binary search tree, which way it goes, but it does not matter. So when you have a binary search tree, the 3 goes in, we see it goes here because it's smaller than an 8. The 10 is smaller or is larger than the 8, so it goes to the right. And then say you put the 14 in, it comes in, it's larger than the 8, goes over, it's larger than the 10, so it goes over to the right. But in the case of the 3, we put in the 3, and then we put in a 1, it goes here, it's less than the 3, so it goes to the left. If it was 4, let's say down here, but this hadn't populated left, then it would go to the right. So hopefully you can intuitively see that the binary search tree follows a very simple pattern. It's just creating a new node, and each node has 2 children, a left and a right, a less than and a greater than. greater than or equal to in the case we'll be doing. And as you populate it, it's just going to keep traversing down. So the same set of numbers populated in a different order will conceptually yield. Remember, this is a data structure, an abstract data structure that is often memory space, but conceptually on paper, the arrangement is different. And indeed, the pointers would be different that you have, but it always will arrange it like this, where the smallest ends up on the left side. So what, if you were going to search this, kind of be it its name, a binary search tree, Patrick, that was a great answer. Smaller numbers go on the left, larger on the right. By nature of this, anybody, what does that allow us to do? What sort of strategy does that allow us to do to make something more efficient when we have something divided like that? This isn't splits the data, yeah. So what does that allow us to do? The way it's got the data all split. Each time that we traverse to a node, if we were looking, let's say, yeah, searching is more efficient. So if I'm searching for a 7, we know that a 7 is going to be less than 8. So it's going to go to this side. Now, we get here, it's a 3. We have to keep traversing the tree. Yeah, Michael, that's what I was looking for. Divide and conquer, exactly. Each time you're having it, so we know you're theoretically having it. So in this case, nothing else that could have possibly populated here. Say this wasn't a 1 and we were dealing with much larger numbers, and this was a very, very, very large, dense tree. On average, you are committing a divide and conquer each time that you go one step further down the tree while you are searching for a value. And as divide and conquer, what runtime, what big O notation is associated with that? Jacob typing quickly. Yes, sir, O to the log n. That's always going to, when we have a divide and conquer, in its most basic sense, it's an O to the log n. Very good, and that's a pretty efficient time, and that's pretty desirable. Anybody have any kind of 101 questions on a binary search tree? Yeah, if it's splitting it in half, it's usually that. You could go out there and do something to the algorithm that could change that. But overall, if you were following a divide and conquer in general, and I can't think of an example off the top of my head, that might be a good question for the Q&A, or I'm going to look more into that now because I thought of that earlier and did not look it up. But I'm sure you might be able to come up with an example that wasn't. But yes, general divide and conquer, log in, divide and conquer is always preferred over straight traversal or any other more complex method of searching through something, being able to, I won't say iterate, because iterate kind of implies that we're going over each element, but traversing over a data structure. So in this case, each time, if we're looking for a value, we're doing a divide and conquer, because we know go left, right, and we can just keep going down the tree. This tree, you can see, you'll see in a benchmark that we do later, how large you can make these conceptually and numerically. Wait to see what Casey's saying, and I'll move. So are trees generally represented as a collection of nodes with pointers like the linked list? Yes. How it's working under the hood, that is very much, how it's working with the pointers. Obviously, when we say pointers and when you get into C, you're going to, some of you have some background in this already with pointers, having to deal with memory allocation and some of the more low-level things that you deal with in languages like C. But you will see indeed why we call these pointers, why we call it pointer in a linked list, because literally in C, like I said before, 1 or 2 times, we're dealing with a reference that is a pointer to a space in memory. But yes, you can think of each of these as a node, and we will code it out that way, a data point. And each node has 2 children. Each child is a node. Each child of that has 2 children. And you'll see when we implement this really simplistic binary search tree, if you haven't already done it, you're implementing a binary search tree in a lot of more complex methods today. We're going to make a simple binary search tree data structure and one method on it today. And then I'm going to show you some benchmark code and run the benchmark code just to demonstrate how efficient this can be compared to other options. So were there any other questions or comments off the top here from the video or about anything we've gone over previously in the week, the linked list, the doubly linked list, the queue, now the binary search tree? Good questions, good participation coming in. So like I said, today's going to be a little bit more heavy on that. We're going to go over some concepts like we've been doing, just try to solidify everything because the code isn't all that complex. And the benchmark code is something I was actually supposed to give y'all later on for you to use yourselves, but there's no harm in me showing it because it's just meant to be able to show you something later. So I've got some example code of my own that I'm going to run it with the same way I did yesterday. Anybody else? Can anybody off the top of their head before I start coding think of, it's very efficient to traverse this binary search tree, much more efficient than iterating one by one, element by element over a list. What is a trade-off that we would get with a binary search tree overall? In creating it and traversing it, doing a search, what is a trade-off? Something that, let's say, a linked list or a list, a Python list, an array, a JavaScript array, would do more efficiently. Doesn't have to be necessarily with the search. What's something, though, that it could do more efficiently, intuitively, even if you don't know the answer, intuitively, what can you think of? See, Jacob's typing. Yes, searches are very fast even as input size grows. Can you think of something that's less efficient about a binary search tree? I'll kind of narrow it down. When we're populating a list versus populating a, yeah, good answers. And the basis of all of it, even when you are, let's say you had initial values to populate it with, we're going to see it basically works via an insert, like Audrey is talking about inserting an element or adding, deleting things. And why would this be less efficient than populating a list one by one, element by element, index by index? Yeah, you have to maintain the order. So like I said, we can populate this in a different order, but if we're adding to the end of an array, we're simply adding one more operation each time. But when we're populating this binary search tree, when we're inserting into it, we're just not inserting at the end, appending at the end. We're not just popping off of it if we're removing an element. We're actually having to go through and traverse over the tree. Now, that is very efficient, but up front, you do spend more, you spend more up front in terms of operations, and that's something to keep in mind. Just a little side note. Any other questions that have come up? I'm going to go ahead and get to the code. So today we're going to implement in Python a very simple binary search tree data structure. You will see just how simple it is actually, because I'm going to kind of talk through it and have everybody brainstorm it with me a little bit of the Poly's problem solving concept. So I think we're going to first implement a binary search tree and using a class like we've been doing with Python. And once we do that, we're going to insert into the binary search tree. I think by what we've just discussed is the problem. The first step is understand the problem, be able to define the problem, say it in your own words is a good way I like to think of it. Does everybody understand what a binary search tree is and the implications of inserting into that tree like we just discussed? The lack of efficiency in doing that, but the overall efficiency in being able to search it, which is very much often something real world applicable that we're looking to do. If somebody doesn't understand it, please speak up. Okay, so we've got the problem defined. I'm actually even just going to make a poll real quick and make it anonymous, and I want everybody to answer it. Video. Okay, sorry about that. Does everyone understand how inserts works in a search tree? And I will make this anonymous. I will just say yes, no, maybe, so. Everybody answer this survey real quick. It's anonymous. Send a channel. Everybody understand how the insert works? How do we have to continue traversing? No. 2 no's. Okay. So if we're going to think about it programmatically, let me go back to the picture. We start with a root. The root can be anything. Let's just say if we have a large set of numbers, maybe you pick the midpoint. If you had a way of knowing what the midpoint was, or if you had a way of knowing, just so it would be we speak about it balancing a tree. If you'd be able to balance the tree, you would obviously want to idealize your root. But in this case, let's just say we've picked a root, because either which way we're going to pick a root. Now, when we insert into the tree, remember, less than goes to the left, greater than goes to the right. So if we insert a 3, programmatically, logically, we're having to ask, is 3 greater than or less than 8? It's less than 8, so it goes to the left. Then let's say we insert 1. This is full. Is it less than or greater than 8? It's less than, so it goes here. Is it less than or greater than 3? It's less than 3. This is empty, so we create this node. Then say we insert a 6, less than 8, but it's greater than 3. This is empty, so we insert the 6 here on the right. Then we insert the 7, less than, but it's greater than, so it goes to the right. It's greater than, this is open, so it goes to the right. If we insert the 10, it's greater than immediately. So we're always just looking, is it greater than or less than? Is the left or the right, depending on where it needs to go? Does it go to the left or does it go to the right? Is it less than or is it greater than? Is the space full? If the space is full, repeat the operation. Does it go to the left? Does it go to the right? Then is the space full? If the space is open, then we can create a node there. If the space is full, we move to that node and we repeat the operation again. So let me ask one more time. All right, everybody vote. We got more people vote. Do you understand or not how we insert into the binary search tree? We don't want to move on to the second step. One more person hasn't voted. Everybody vote. All right, I'm going to go ahead and move on. I'm getting a lot less no's. One person hadn't voted, but everyone is voting yes. But we'll just keep that in mind as we move forward with the code. So Open this up. Give me 1 second. Like I said, we're going to implement it with a Python class. And first thing we're going to do after we put the class definition there is we're going to have our init and so we're just going to say self.value equals value. We've taken that in as a parameter, and that is simply the value that we've got, the numerical value, the integer that we're putting in. What would we want to also add to here? Remember how we defined each node? Each node had something. What would we need to define here as well? Yeah, the left and the right. So we'll just say self.left, and when we initiate it, it's none. And self.right, equals none. And so why does the tree itself have a value? Isn't that only the node that has it? But you're going to see it. That's a good question, Jacob. The binary search tree is, you'll see it down here as we're inserting each node, the way that we're doing it. You could go about doing this different ways, but let me pull that back up. Each node is the binary search tree class. Does that make sense? We're just creating, you'll see right down below this, we're just creating a new instance of the class for each node, and each one has a left and a right. It makes a real simple, intuitive way. Once you realize what's going on with it, I think I had the same question the first time I saw it way back. But yes, each node is simply an instance of that class, and each node has a left and a right. It may be none. It's always initiated with none. Did that. Cool. I'm going to let Michael type. Let Michael type, and I'm going to go ahead and go back to the code while we're doing that, and I will start typing. We're going to make the insert method, and with the Python syntax self, if anybody sees me make any mistakes with colons, spacing, anything, a couple people are typing, so I'm going to let y'all type real quick before I get started on the insert. We've only got maybe about 10 lines of code to do this, so definitely want to field the questions. Start thinking about, though, if you're not writing a question, what we would need to do inside this insert. Yeah, I caught that. Thank you, Patrick, while I was waiting. What would we do once we inserted a new value? Remember, I was talking earlier, okay, we've got the 8. Now we insert a 3. What do we have to do when we insert here? Boom, the 3's coming in and it hits here. What do we need to do with this node, with this value that we're getting? Actually, we're just getting a value. What do we need to do with this value at this point as it begins to be inserted into the tree? Compare value to self.value. Exactly. So we can say if value is less than self.value, what would we do here? If value is less than self.value, what are we going to want to do? Insert to the left, yes. Yeah, we do. That's a good point, Rachel. We need to see if there is already a self.left and then insert it. So if the value is less than self.value, we can say if not self.left, just going to be a Boolean given a true false. If not self.left, we'll just set self.left equal to, and right here you see what you were asking about earlier, and we're just going to put the value in there and make a new binary search tree. Else, if it exists, if there's already a node in that place, what could we do really easily programmatically? Self equals Patrick, I'm not sure where you're typing about. Well, yeah, we would want to traverse left. We would still want to traverse left, but what you could do in the else statement, now I see what you're saying, is self.left.insert value and just repeat the insert. And that insert will just recursively call itself until it reaches an empty spot that it can instantiate the binary search tree value. Does that make sense to everybody? So we're just recursively calling insert on itself until we get to an empty space. So if there's not a self.left immediately, it assigns self.left to the instance of that binary search tree with the value we're inserting. Else, it just recursively calls itself and it continues to do that. And this is where the lack of efficiency compared to populating a linear list, a Python list, comes. You're looking for an empty leaf space, basically. Exactly. That's exactly what you're doing. Then we can just say elif value is greater than or equal to self.value. And what will we probably want to do here? It's not less than, it's greater than, equal to self.value. What are we going to do here? Michael's typing. Yep, need to go to the right. So we can just do the same thing we did up top. If not self.right, self.right equals binary search tree value else, and we just do the same, and then we make that recursive call self.right.insert to keep traversing down the tree until we find that empty leaf space. And that's all there is to it. I want to do a poll to make sure everybody understands this. Make it anonymous. Yes, no, sort of. Everybody answer this. And if anybody's wondering, yes, I'm aware that I pulled the participants up and screenshotted it. That's how one of the ways we're keeping track of attendance. So that was no accident. Yes, good. Everybody vote. We got some more people to vote. Does everybody understand how this is working? We're simply comparing the value, and then we're recursively calling the insert function if that space isn't available, so we can keep traversing the tree until we have an open space to put it. Just looking left or right. Is it greater than or less than? Does it go right? Does it go left? Is the space open? Is it not? If it's open, assign it. If it's not, recursively call the insert. Awesome. 8 yeses. So today you are going to be implementing various methods. I don't have them right in front of me. I know you're going to have a contains. Should be able to delete a value. You should be able to, I think the wording is you just have to be able to traverse the tree in some manner. So it's going to give you the option. You could traverse it in many different ways. And there are two very common searches that are performed. One that's called a breadth first search, that if you can think of it conceptually like we're looking at things here, a breadth first search, always think of it left to right. It's checking each level first. A depth first search penetrates all the way down and continues to do that until it reaches the end. And the idea of these searches is that you never touch the same data point twice. But that probably all will become a little bit more clear as you look at the repo if you haven't already gotten there. So today you'll be implementing that. Something interesting to discuss here, and like I said, this is implementing divide and conquer. So if we had a list and we need to do a contains on the list, what runtime is that going to be on a Python list? On average, the runtime. What's the O to the big O of checking if a value is in a list by nature of how we have to look for it in a list, by nature of the data structure of a list? What is the runtime? O to the n, exactly. Each element you add, the worst case is that you have to go to the very last element to get to it. Best case, it's one time because it's the first element, but on average, which is what we're thinking here, we are going to have O to the n time with this binary search tree. As we said earlier, we have O to the log n time because we are dividing and conquering. The divide and conquer is hard to see here in this simple tree because it's so simple, you're really not dividing and conquering a lot of the times when you're eliminating choices. But something we can look at. So today you'll be implementing this binary search tree like I've got some code for here. There's this benchmark file. Can everybody read this okay? Or do I need to blow up my text a little bit? Somebody let me know if they need me to make it bigger. I want everybody to be able to read clearly, and I always forget to ask because nobody says anything. But looks good to you. Okay, well, if nobody has any problems, if somebody has a problem, speak up. If not, we're going to keep it like this because we can get more on the screen. This piece of code is something we're just supposed to drop to you. I will drop it to everybody. Go ahead and drop this binary search tree to everybody right now. Just looking it over to make sure that it's Mind went to sleep there for a second. Says of type Python. Okay, can everybody hear me okay? Somebody type in the channel just so I can make sure. It looked like that took a while to upload, so I'm thinking my internet cut out, but I see y'all are typing. Cool. Okay. So we have this file, this benchmark file, and it's just something we're going to give to you, but I'm going to kind of go through it line by line, ask some questions. I'm going to describe basically what this is doing. It's got some notes in it that this is just going to benchmark. The idea of this program is to benchmark the average time it takes to traverse a list that we are going to generate, very large list that we're going to generate with 100,000 elements in it, and a binary search tree that we're going to implement also with the same amount of elements in it. We're going to kind of quasi implement it in the same order, if you would, but you'll see what I'm talking about later. So we're going to implement a very large data structure, and we're going to run each of them 500 times, running a random search for a value that is in that structure. And we're going to get the average time, so that what we are trying to show here is that the binary search tree is much, much more efficient than the list. So the code that they give us, it's importing time so that we'll be able to do the start time and end time like we're doing here on line 17, 19. Importing random, we're going to use that quite a bit to generate some random integers that you'll see here in a second. So we'll use that module several times. And then from binary search tree, which is all on my desktop, so I can just put it this way, binary search tree, it's on the same, in the same directory. When I look here, I've got my BST and I've got my binary search tree and my benchmark.py all in the same place. And then I've got a print statement that I added in here just actually when I was testing it for another time earlier, because it does take a second to run. And so this is the average time it takes to check containment of a random value in a list over n runs. And it might not be self-explanatory at first what these parameters are, but we're going to invoke all of them down here. So the N, the L, and the B that you're seeing, the L and the N, the B and the N, we'll define the N runs makes more sense, but we will be defining all of that down here when in the main when we actually run it. So just bear with me if there's any, if it's a little bit confusing at first. Remember, we're getting an average time, so we're going to initiate a variable total time and set it to 0. Line 14 for underscore. Why do I have an underscore there? We talked about this yesterday. Why would we do that in Python syntax? You don't have to. It's not going to throw an error, but why by convention do we do that? Why do we have an underscore in line 14? Yeah, we don't need a reference to it. We're just simply iterating for the sake of needing to iterate. So it's just a way of notating that we don't need to put for I in range or for num in range or for whatever in range. We just put an underscore there by convention. It will function otherwise. And we're going to go from 0 to n runs. When we have the range 0 to n runs, where does it include, if say n runs is 100,000, does it include or not include that 100,000? Inclusive or not inclusive in Python? This is a little bit of an important fact when we get down to line 15. Another question I'm going to ask. Inclusive or not inclusive? Does it go from 0 to 100,000 or 0 to 99,999? Anybody? It's not inclusive, so it's going to run from zero, the zero index. We want to run it from zero, and that is the starting point. And it's not inclusive of the endpoint, so it'll run to 99,999 in our case. That is important because that means we can have, if we say, remember, we're doing this in a for loop, so this is just going to keep repeating itself. We need a random number. We need the random number because we need to be able to pick a number between 0 and 100,000 in our benchmark that we're going to look for. They're all going to be in there, as you'll see later on. And so this random number needs to run from 0 to n minus 1. Random num equals random.randint. This is why we imported random. Randint generates a random integer from 0, inclusive in this case. So this one is not inclusive. This is inclusive, n minus 1. So we need to put n minus 1 and not n, because theoretically we could end up with 100,000 here if we just used n. And remember, this has 100,000 elements, but it's from 0 to 900, or excuse me, 999,999. It starts at 0. This will start at 0 and also needs to end at 99,999. Excuse me, I'm getting my tongue twisted there. So that's just a little detail. It's minor, but one of those that's worthy of pointing out while we've got time. Start time equals time.time, Python syntax to invoke this time that we have brought in. We'll say random num that we have generated in L. L is the list that we're going to give it here. N is the size of the list. And this number of runs is how many times we're going to run it. That'll be 500. Remember, we're going to actually populate all that down here if this isn't making sense. So we just basically have a list that we're going to generate later that we will feed this. We have how big that list is going to be, how many runs we're going to do. We've generated a random number that is in that list, and we just run a time. We run this Python syntax random num NL. This will return true, false. Obviously, it's going to have to iterate over the list to look for this. In time is time.time. Remember, we're doing a benchmark, so total time was 0, and then you'll just say total time plus equals end time minus start time. And that will give us the total run time, and we're just getting the total because once we're done in this loop, however many runs that we're doing in this loop, we're going to return total time divided by n runs. Like I said, this is beyond what we needed to cover. And I've already done attendance, dead honest. If you don't want to listen to this and you want to get started on your code, feel free to. This will probably only be another 15 minutes or so, but if you'd like to go, this is something I'm going to drop in the channel that's supposed to just be supplied for you. I just wanted to run through it so that we had something to cover since the code was so short. And we covered all the concepts. But I'm going to ask, does this make sense to everyone? And I'll make it anonymous again. Everybody vote if you would. Sort of. Got 4 and 4. I'm going to run through the next one, which is pretty much the same, and then I'll kind of put it all together at the end, and then I'm going to come back and ask, and it may be more clear. But all we're doing here is we're benchmarking the time of a list L that we'll take in as a parameter down here, of size n, which we will take in as a parameter down here, a list that's n long, n number of elements, and we're going to test this n runs number of times so we can get an average runtime. Obviously, if we just run each one once, we're not going to get, depending on where it's located and how the structure with the binary search tree, how it falls, we need to be able to get more than a few runs to be able to get a good average of that time. So we just have a total time equals 0 because at the end we divide total time by n runs to get the average. We generate a random number between 0 and n minus 1 because we are working with zero-based lists. So we're running from 0 to the same. This is n minus 1 that this can run to. Remember, this is not inclusive. This is inclusive with the random n. Just invoking the time, we're saying, hey, is this number is in the list somewhere. So this is going to return true at some point. How long does it take to find it? That's what we're doing with start time, end time. Then we're just adding that time to the total, and then we're just dividing by at the end to get that average. Same thing here with BST. We're taking in a binary search tree of n size for n number of runs. We start with a total time. We iterate the same way. We generate a random number the same way. We have a start time, and once again, we're just going to use a b.contains random num. And this is not a Python function. This b.contains is something that you will implement today. B being down here, you'll see a binary search tree like we implemented earlier. This contains is another method you will implement, and this is going to also be run with the same numbers as above, so we'll be able to compare the two. And so we have an end time, then total time plus equals the end minus the start time, and we return that total divided by the number of runs, just getting the average. Where all this might make more sense now, in the main that we've got, we set n to 100,000. We want 100,000 elements in our binary search tree, 100,000 nodes, data points in our binary search tree, and we want 100,000, or excuse me, 1 million. 1 million nodes. I keep misspeaking these numbers, but 1 million nodes. Random.seed. Does anybody know what that does on line 49? This is a little obscure. I had to go back and actually look at it to check this out to see what it was doing. Anybody happen to know what the random.seed is doing? Michael, hopefully we got an answer here. Yeah, and remember, because in here, within here, we're calling this list bench and the BST bench, and we're doing this random right here. We're also doing a random.shuffle in here. So yeah, you have to initialize the random number generator, and it's simple syntax that in this random generator that Python has elegantly built for us, you have to use random.seed. If you include nothing in here, if you include, I think you can put a number, and you may be able to put a character as well. It runs the Python hash function on it. That seeds it. If it does not, it seeds it with the atomic time, or if there are any operating system parameters that are available, I didn't look into what those are, then it seeds it with that. All you really need to know here is that if you're going to use the random, you've got to seed it like we do here. And then we have the L that might have been confusing here, the list. We are making our list. So we say L equals, and with Python syntax, we're just setting the brackets for the list, and we're populating it I for I in range 0 to n. Remember, this is non-inclusive, so it won't be a million. I think earlier I was saying 100,000 and then 99 or whatever. It's a million. It will be 999,999. So a million elements, but we have a 0 index. And that's what we're doing here. We are making a list of 0 to 999,999. Then with the random.shuffle, and we put that list into random.shuffle, and this does an in-place shuffle of the list. Why would we want to shuffle the list? Somebody answer before we move on. Why would we shuffle the list? Yeah, it's in order initially. So by nature of what we're trying to do here, we need to be able to shuffle it. So we shuffle the list. Keep in mind, this is the same list we're going to use the entire time. Each time that we use either the list or the binary search tree, there's 500 runs of it. When we call this DST and list bench, we're going to call it with 500 runs right here that we actually type in. Each time we generate a random number between 0 and 999,999, every single value that is in our list and will be in our binary search tree, we're going to find a random num, run it against there, and by running different random numbers against this list in this binary search tree, which the order of the list and the binary search tree, the structure of it will remain the same, we'll be able to get that average time, okay? B equals binary search tree, and then we got in here, we're going to remember each, in the binary search tree, each node is a value. So in this binary search tree, the way we're wanting to generate it, we're going to generate it from 0 to 999,999. Same amount, same values that are in the list. We've got to have, what do we have to have with a binary search tree initially? What does a binary search tree start with? Yeah, a root, an initial midpoint node. So what are we doing right here? And we've got 2 forward slashes in the 2. What type of division does the double forward slash indicate? And this is working because we've got a range of numbers that we're dealing with, 0 to 999,999. What does that double forward slash in Python specifically do, as opposed to a single operator, the single forward, drop the remainder? Yeah, it floors it. So no matter what it is, it can be 3.9999999. It's a flooring operation to get an integer. This is picking the midpoint, as Matthew mentioned just a second ago. So from this midpoint, then, we are going to go from I in range 0 to 999,999. What's something kind of a little bit weird about line 55 and 57? We picked a midpoint, and now we're going to pick every element in that range, the same that we did. There's one kind of odd thing about it. Doesn't even really matter. It's just something that popped in my mind. You actually are going to have one additional element here because we already picked our midpoint. So that's going to get regenerated right here. But we've got a million elements. Obviously, statistically, that's not important. And then they kind of have some weird syntax here. I had to look at this a second. B.insert L of I. What are we doing on line 58? It's our last line of code, really, that we got to think about. Can anybody think what we're doing on line 58, why we're doing it like this, and why we're just not putting in I? Because I is going to be the same. Why are we using L of I instead of I? Yeah, Matthew, there is definitely ways that you could skip it. You are most certainly correct. This is code right here that I had nothing to do with and that I have not touched, other than I put a print statement up here. This is code that's to be supplied to y'all as is. I just wanted to run through it with everybody so that we had something to do for the entire hour. Yeah, we've already generated this list up here. And all it's doing is it's pulling the value at L and I from the list and inserting it. And in this case, I, the index I and the value are both the same. So just kind of a little bit of a weird syntax that they put in here, but let's see what Matthew typed. What is it doing? There's a reason that they're doing this, though, conceptually at least. Remember, our list has been created, but now we've shuffled our list. So once we've shuffled our list, the indexes and the values no longer match. What could they be thinking here on line 58? Why they just don't insert I, they insert L of I. Remember, they don't match anymore after the shuffle. Yeah, it's going to end. When you populate the tree, you're going to just populate it. If you populate it, if you just used I, yeah, 0, 1, 2, 3, you would just be dumping the numbers in like that, and they would go in very, I don't know what the word exactly I'm looking here, very symmetrically. You're populating the list. Whereas now that we're populating it based on the index, we will get, by nature of the fact of how that list is set up, we will get every value inserted into there, but we're randomly, it's introducing some randomness into how we're populating the tree. So we don't have a tree that looks quite so symmetric, and theoretically we are testing against the same insertion order of the list and the same insertion order of the binary search tree, even though the two of those aren't directly related. If that makes sense, good. If there's any questions, I'd be happy to answer them. Now that we've gone over this and you kind of make sense of where the B and the L and the N up here are going, I'm going to make this one more time and just ask. And anonymous. Say yes, no, sort of. Everybody answer this. Awesome. Got a few more people in here. If anybody else, yes. Okay. So yeah, I wanted to go through it the way I did, but I'll be real honest. Most of the time, I can kind of just look at code at this point, especially code that I am working with or that I've worked with before, and just understand it without even really having reviewed anything. I had to look over this just a little bit because it had confused me up here what this was doing. And I think last time I just actually distributed this code to the students because we did it a little bit differently. But yeah, all we're doing is implementing a very simple test to benchmark the times, and we're taking all these values in, but you don't see it till here. And then in the print statement, you see list contains average runtime. We're just running list bench with L, the list that we've made, N, the million that we have decided upon, the 500 runs, and of course we're going to do it the same N and 500 in the B, the binary search tree that we've made. We've floored it to pick an initial midpoint because we're dealing with 0 to 999,999, and then we're inserting everything in that range. You end up with the extra element. Like I think Matthew pointed out, there would be a way to skip the midpoint, or you could check. Makes it a little bit more inefficient to do it because you're having to perform a check every time. At least the way that I'm kind of conceptualizing in my head to do it without it, and kind of what Matthew was talking about it. But still in the big picture, not a big deal. But that's what we're doing there. And we're just going to have a print statement to see here. Does anybody have any questions about anything in any single piece of this syntax that I've gone over? I kind of asked a lot of Python specific stuff. I don't tend to do that a lot when we're doing these, but because we had the time, I wanted to go over some of the stuff, especially some of the more obscure stuff. It's a good chance to go over it. So nobody has any questions, we can actually go down here. If we got everything right, remember we've got our binary search tree here that I've implemented. that you will implement later today if you've already not done so. And we can just look, and we are in the desktop, and I can say Python 3 benchmark.py running. Please hold for operations to complete. This does take a little bit to run, because remember, we're iterating. We're doing 500 runs of the BST, 500 times the list, and each of them has a million elements. So we've got to populate that, and then we've got to search through that, either using the built-in Python random num NL, which is a Boolean, or b.contains random num, which you will implement later. So I actually added that in because I controlled C'd out of the whole thing and put that in there to make sure there wasn't a bug, because it took so long to run. But if we're just patient with it, I'm going to drop this code for you as well. And there we go. And we see here, list contains average runtime 0.04 seconds. BST contains average runtime 1.98 e to the negative 5 seconds. So we see that BST is exponentially more efficient in terms of seconds. This is not directly time complexity because we're measuring operations in time complexity, but a lot of times we use the time in conjunction, and they most of the time are very closely related. So you can see that that BST is much more efficient because we're using a divide and conquer. We're getting log in time on average instead of in time. And we implemented a test using the structure that the basic structure that we showed here in BST, the insert. You'll actually have to have the insert in yours today. And then over in the benchmark, we're just importing this search tree that already has the contains. Anybody have any questions about anything from this week, anything from this code? We're about an hour into it, and that's all I've got. Like I said, originally I'd like to keep these to about an hour, but I'm not going to, what's the word I'm looking for? Not necessarily going to limit them to an hour if we need more time, but some members of the instruction team felt that an hour was the best time to run these guided practices, and today it just kind of fit perfectly into it. Like I said, with the benchmark, it's just supposed to be something that you receive. If there's some little detail of it you don't understand, go back and look at it. You can shoot me a DM. I understand this code top to bottom, everything that we've just implemented, the search tree that you're implementing. But I just wanted to have time to be able to go over some stuff that we normally wouldn't be going over. And it looks like by what everyone answered, everyone understands the basics of the BST, how it inserts, how it functions. You got to see the benchmark it gives it against the list, and we got to go over some runtime, think through a little bit of the polyas problem solving, got to go over some Python syntax, discuss some other data structures. Does anybody have anything, any questions whatsoever right now? If not, I'm going to turn you loose. Get back going in the repo. You got 45 minutes until lunch. Tomorrow, do not fall behind tonight. The heap is the most complex thing that maybe somebody, it just clicks for them more than anything else, and it's not. But in general, the heap is considered the most complex thing that we go over for the week. That's tomorrow, so you want the day to work for it if at all possible. Does anybody have anything, though? I hope this was helpful. I know it gets boring at times, just me throwing all those questions out and talking and not sitting there typing code and soliciting, hey, what should I do next? But sometimes when time permits or when we don't have a lot of code that we're actually doing, I want to take the time to go over specifics like that. Be able to stop like I did step by step. Hey, does everybody understand this? If no, kind of iterate back over what Michael type. Yeah, I like this one. And something that, to be dead honest, that Lambda as a whole is, for lack of a better term, struggling with is how to format these GPs. Um, I like this. And the feedback that we got from last time, this is a little bit different, but I like how this kind of went today, where there's some concepts, there's some interactiveness with the code. I'm able to field questions. We're able to stop. Does everyone understand? Okay, maybe somebody doesn't want to speak up. Let's throw a poll in there. But we don't spend 2 hours doing one singular thing, or 2 hours just, mucking through some concept. So I liked this as well. So I hope a lot of you found this helpful. I've got all the code dropped. You know what you got to do. If you have any questions, talk to your PM, talk to me if you're not with me. I will make this video. You've got a copy of all of Sean's videos from these, so feel free to review those. I'll drop this video. I didn't actually get to put the video up from yesterday because something corrupted in it. I've never had that happen before, and I wasn't able to do it, but we had Sean's videos as well, so of course he does an excellent job of doing all of these. But I thank everybody for your time, and have a good day. Enjoy your lunch. I will get this video processing and get it posted in the channel. And you've got your video for tomorrow that you need to go over with the heap. And like I said, I would recommend getting a head start on that if you can. But right now, worry about MVP and the BST and the methods that you're supposed to implement that's in your repo. So, thank you.